let's review the part that we did last time. So we talked about the Dirac Delta, and basically the Dirac Delta, we will take it to mean that it is something. Okay, it is not really a function in the ordinary sense, but we will deal with it as if it is a function. And more importantly is that its impact is seen when it is coupled with another function under the integral sign. So basically this is like, you can take sort of the definition that the integral from minus infinity to infinity delta t h of t dt is h of 0. Again, you can take this as a definition. And delta t, we showed last time, for example, a proof that if you define something as such, then delta t cannot be an absolute integrable function on a finite interval, and so on. But we will treat basically this integral as if it's true, and we will apply like ordinary calculus. So again, integral from minus infinity to infinity, delta of t h of t will give you the value of this function here at 0. So this is a function, we'll assume that the domain is R, and so it has a specific value at t equals 0. And basically it doesn't harm if you limit your domain of integration, so long as it includes 0 as an interior point. Then you also get h of 0. So the most important thing is that basically we ask ourselves, what is the value of t that makes, or the values of t that make the argument of the Dirac delta equal to 0? In this case, it is t equals 0. And so this is what is important. So if your integration limits include 0 as an interior point, then the Dirac delta is active, and you still get the same result here, which is h of 0. Okay, so the effective values of t, that are basically important when we deal with the Dirac delta, are the values of t that makes the values of t that make the argument of the Dirac delta equal to 0. And we use this like if we do a composition of the Dirac delta with a function. So the first order of business is to say what are the solutions to basically the equation phi of t equal 0. Okay, so this is basically the equation that is important, from which we can obtain the values of t that will be like important in obtaining our results. Okay, and so delta phi of t, under some conditions, it is given by this. It is basically a bunch of Dirac deltas, and those are shifted to tj's, and each one has an amplitude which is 1 over the absolute value, or the derivative of the function at tj. And so we are assuming that phi of t is differentiable. Okay, and so basically it makes sense to talk about its derivative. Moreover, if you remember basically the steps that we tried to do to justify this expression, we needed the first derivative of phi of t to be a continuous function. And the reason for this is that basically you go and solve this equation. You get t1, t2, t3, at which the function phi of t is equal to 0. At those t's, it must be the case that basically the first derivative is not equal to 0. And we are dividing by it here, and so it is important really that the first derivative are not equal to 0. But more importantly, during the derivation itself, the fact that at those points, the first derivative is strictly positive or negative, and if coupled with this extra assumption that the first derivative is a continuous function, this will mean that the first derivative is strictly positive or strictly negative on an interval about t1 and t2 and t3 and so on. So the function around t1, t2, t3, and so on will be locally invertible. Okay, it will be like either monotonically increasing or monotonically decreasing, and this allowed us like to do a substitution of variables in our integration to obtain this result here. Okay, so this result is very useful, but of course, it has basically some assumptions there that basically you need the function to be 0 at those t's, but the first derivative should be positive or negative, but never equal to 0, and the first derivative as a function should be a continuous function. Now, in signals and systems also, we need like sort of a function with the Dirac delta without integration, and in this case, the Dirac delta is as is here. It is left intact. And what you can do is that you can replace this function of t by the function evaluated at the location or position of the Dirac delta. The Dirac delta is designed to be infinitely differentiable, and we can define basically the effect of its nth derivative as basically if it's coupled with some function h of t under the integral sign, it gives you the value of the nth derivative of the function, assuming, of course, that it exists, evaluated at t0. And then, because typically this is done using sort of integration by parts, there will be an alternating sign, and we will have to use this factor -1 to the power n. Now, in signals and systems, and especially when we take Fourier analysis, we will talk about differentiation, and there will be a rule for differentiation that is very useful. Now, in signals and systems, we do not use, in many cases, the classical concept of differentiation. So if you have a function that has a jump here, so you have a function, and this function, it has a jump at t. So assume that it is constant. It is some constant a below t0, and then it is some constant b above t0. And, a is not equal to b, indicating that there is a jump. There is a discontinuity at t0. Now, classically speaking, the function is not continuous at t0, and hence it is not differentiable at t0. However, in signals and systems, we will actually say that the first derivative of this function, okay, so away from t0, the first derivative is equal to 0, right, because it's flat here and there. But there is a jump, so we will take the derivative as if it's generating or giving us a Dirac delta at the location of the discontinuity. Okay, so in this case, we will not say that this function is not differentiable at t0, which is the classical result. We use a concept called generalized derivative. Okay, and it is a concept, by the way, that is defined in a rigorous mathematical way. And interestingly, the generalized derivative is defined in terms of an integral. But again, let's not bother now for the details. For us, if we have a function with a jump, then the derivative of the function will include a Dirac delta at the position or location of the jump. And the amplitude of this Dirac delta will equal, basically will be equal to b minus a. So this means that if x of t is constant and it is differentiable, everywhere except at the jump, then the derivative will be the classical derivative in addition to this Dirac delta. Okay, so for example, if your function, suppose that your function has here slope 1, okay, and then there is a jump, okay, so this is a, this is b, and there is a chunk here, and this is also is a slope one, then the derivative, so the derivative will be equal to 1, okay, which is like the classical derivative at all points except at the point of discontinuity. But here in signals and systems, we will add it's 1 plus p minus a. You know, again, if this happens at t0, this will be delta t minus t0. Okay, and in Fourier analysis, this is very important. Like if you do not consider this Dirac delta while applying the differentiation rules of Fourier analysis, you will get wrong results, because basically those results or theorems are assume that you are using the concept of a generalized derivative. Okay, so this is very important. And like one thing here, so if you have the Heaviside unit step function, the continuous time unit step function, so it's a derivative according to this thing here. Its a derivative will be, so it is constant below 0, it is constant above 0, and there is a jump, it goes from 0 to 1, so it is delta t. So this is actually something that we will treat as true. Okay, du of t by dt is delta t, despite the fact that, again, like classically, we will say that the function is not differentiable at t equals 0. But here it is, we'll take it to be differentiable. Again, we are using a notion that is well defined. It's called a generalized derivative. Okay, so keep this in mind. And this is one thing like in which the Dirac delta is useful. Now, the thing to do with the Dirac delta is to investigate what happens if we don't have integration and we have a derivative of the Dirac delta. So what is x of t multiplied by the nth derivative of delta t minus t0? Let's focus first on the case in which t0 is equal to 0, so we don't have any time shift. Okay, and again, the story is that if you want to investigate something like this, you multiply it by a function. It's called typically the test function, and then you see what is the impact. So if you take this x of t, the nth derivative of the Dirac delta multiplied by 5t, then you can write this as an integral with the nth derivative, and now you have this product of two functions, which is a function. And according to the rules, if you have a function here, so you can think of this like g of t, or here I give it a name here, which is psi of t. Now, if you multiply by the nth derivative of the Dirac delta, then again what you get is the nth derivative of the function evaluated here at t equals 0, and then you have minus 1 to the power n. So we just apply this rule here. But what is function psi of t? So psi of t will be basically this product here. So this integral, so the Dirac delta itself is multiplied by x of t, and then there is this function phi of t in the integration. Then it's as if we have the Dirac delta acting on the product x of t phi of t, and so it will basically evaluate the nth derivative of the product at t equals 0. Okay, so what is the nth product of the, what is the nth derivative of the product of two functions? Okay, so we have Leibniz rule. So basically the nth product is given by summation k from 0 to n. So that the most familiar form is when n is equal to 1. And if you are differentiating the product of two functions, so if n is equal to 1, basically the derivative will be, the derivative of the first function multiplied by the second function plus the first function multiplied by the derivative of the second function. Okay, so what if you are talking about the nth derivative? So if you are talking about the nth derivative, then for n equals 1, you get two terms. For n, for the nth derivative, you get n plus 1 terms. So k from 0 to n, you have nck. Okay, n choose k, which is the binomial coefficient, the factorial of n divided by the factorial of k, n minus the factorial of n minus k, and then you have the derivative of order n minus k applied to function x, and the derivative order k applied to function phi. Okay, so for example, if n is equal to 2, what will be this thing? It will be 2c0, which is 1, and then we will have the second derivative of the first function multiplied by, if the superscript is 0, then I'm talking about the function itself. Okay, so this is actually phi, and then we will have, if k is equal to 1, we have 2c1, and then we will have the first derivative of the function, and the first derivative of the other guy of the first function, and then multiplied by the first derivative of the second function. And the third term will be 2c2, and then it will be x superscript 0 between brackets, which means x itself, and then you have the second derivative. Okay, and so on and so forth. Okay, so this is a general rule, and you can like prove it, like, you know, by something like induction or something like this. Okay, now so this is our result, but this guy here, you know, so this phi k of 0, so this is the kth derivative of phi of t. We can obtain it from this, right? So the integral of phi of t multiplied by the kth derivative of the Dirac delta, it will give us the kth derivative of phi evaluated at 0 multiplied by minus 1 to the power k. So phi k of 0, I can actually write it as minus 1 to the power minus k, and then multiplied by this integral here. So what we will do is that we will replace this kth derivative of phi of t evaluated at t equals 0, we will replace it by integral involving just phi of t multiplied by the kth derivative of the Dirac delta. Okay, and so this is what we did here, and then we can rewrite things. Okay, so this integral here, so this is the thing that we are investigating. We started by investigating, and now we can write this as an integral of something multiplied by phi of t dt. So we will take it to mean that the signal multiplied by the nth derivative of the Dirac delta is this thing that we find inside brackets. Okay, so it will be a sum, k from 0 to n, nck minus 1 to the n minus k, and then we have basically the derivatives of this x, and we have basically the derivatives of the Dirac delta. Okay, so we will take this again to be an equality, that this thing here, this quantity here, is analogous to basically this summation here with n plus 1 terms. Okay, so the trick again is basically combine the x with the phi, apply basically the nth derivative of the Dirac delta, which results in this product being differentiated n times. Use the Leibniz rule for basically the derivative of a product of two functions. Then take the derivatives of phi and express those derivatives as integrals involving phi without differentiation multiplied by the derivatives of the Dirac delta. Then match the left and right hand sides and say basically that this thing here, x of t multiplied by the nth derivative of the Dirac delta, is given by this summation here with n plus 1 terms. Okay, so and you know, basically the same will apply. It's if you add a shift here, basically rather than having this derivative evaluated at t equals 0, it will be evaluated at t0, and those Dirac deltas will be evaluated, or their argument will be not t, it will be generally t minus t0. this is the general formula if you have a function that is multiplied by a derivative of a Dirac delta, and now things are basically in terms of a sum, and this sum will involve the Dirac delta and its derivatives up to the nth derivative. Okay, so this formula, if n is equal to 1, let's say, so n, if you have something x of t, and then the first derivative t minus t0, okay, so n is equal to 1. So according to this formula, we have two terms, right? Because the summation k from 0 to 1. So we have two terms, one with k equals 0 and another with k equal 1. So this is equal to, if k is equal, so n is 1 now, k is equal to 0. So this will be 1 c0, okay, which is equal to 1. And then we have minus 1 to the power 1 minus 0. Okay, so this will be minus 1. And then we have x n minus k, which is 1 minus 0. And then at t0. This is multiplied by delta. Again, if the superscript is 0, we are talking about the Dirac delta itself. And this will be t minus t0. We are not done because there is a second term in which k is equal to 1. So this is 1c1. And then there is minus 1 to the power 1 minus 1. And then there is x of 1 minus 1. Okay, which will be the function itself, t0. And then we have now the first derivative of the Dirac delta, t minus t0. So if we like sort of put refine our results, so 1c0 is 1, minus 1 to the power 1 minus 0 is minus 1, and this is the first derivative. So this is minus the first derivative of the x evaluated at t0 multiplied by the Dirac delta at t0, and then you have plus 1c1 is 1, minus 1 to the power 0 is 1, and so this will be the function itself at t0 multiplied by the first derivative of the Dirac delta t minus t0. Okay, so if you have now the first derivative, then you get actually two, and you are interested in replacing this function by constants, then you need two terms. You will need the first derivative of the Dirac delta. You will need the Dirac delta. The Dirac delta will have the amplitude that is minus the first derivative of the function evaluated at t0, while the first derivative of the Dirac delta will have an amplitude that is the function evaluated at t0. Okay, so this is like the application of this rule here. If n is equal to 1, and of course, like if n is equal to 2, then you will have three terms, right? So because k now will go from 0 to 2, so you need like to have k equals 0, k equals 1, k equals 2, and so forth. Okay, and basically, if the shift is, if t0 is 0, then this is what you get here. Again, you just set t0 to 0, and now if you want like a specific x of t, let's say that x of t is equal to t. Okay, so if x of t is equal to t, okay, then its first derivative is equal to 1. Okay, and x of 0 is equal to 0. The first derivative is a constant 1, and so if it's evaluated at any time, it will give you 1. And so if you put those guys, here, so x of 0 is 0, so this is gone. And so this will go away. Okay, it will go away, and so we will not get basically the term with the first derivative of the Dirac delta, but this one will survive as minus 1. And so we get this nice result that if you take the first derivative of the Dirac delta multiplied by t, what you get is minus delta t. So this is like a nice way of saying that you can write down the Dirac delta as minus t multiplied by the first derivative of the Dirac delta. Okay, and don't forget that basically the Dirac delta is like an even function, because delta of minus t is the delta of t, and remember the scaling rule that delta of at is 1 over the absolute value of a should not be equal to 0. Delta of t. So if you put a equals minus 1, you get delta minus t equal delta t. So it's like an even function. And so if it's an even function, if you differentiate an even function, you get an odd function. And if you differentiate the odd function, you get an even function. So basically, the Dirac delta is even, its first derivative is odd, its second derivative is even, its third derivative is odd, and so on and so forth. So those guys, they have symmetry. If you treat them as functions, they have symmetry. Okay. So and this is consistent what we are, basically. So it's like delta t. This is an odd function. This is an odd function, and the product is an even function. Okay. The first and second, actually the nth derivative of the Dirac delta will allow us to compute difficult Fourier transforms that are not defined classically. Like, what if you want to take the Fourier transform of a polynomial in T? So what if your x of t is some polynomial in T, 5t to the power 7 plus 17t squared plus 7? What is the Fourier transform of this? So you can actually, take the Fourier transform of any polynomial, and it is expressible in terms of the Dirac delta and its derivatives. So those derivatives are important, and they appear, they are not like sort of useless or anything. Okay. Now, we have been talking about signals. Systems also are, so signals, periodic versus aperiodic, power and energy signals, even and odd signals. So also systems are classified. And what is a system? A system is like in mathematics we call an operator. So basically the system, it takes a signal as an input, and it responds. It generates as an output basically another signal. Okay, so a system, again, it's like, think of it as something that you give it a signal, and its output, or sometimes called the response, is another signal. Of course, the system can be as trivial as an identity system, which basically does nothing to the signal. If you give it some x of t or x of n for discrete time systems, it will respond with the same input signal. That's a valid system, by the way. It just the signal is basically reproduced at the output without any change. That's a valid system. There are systems that will do time shift, systems that can do time scaling, systems that can do sorts of different types of filtering, and so on and so forth. But generally, this is a system. A system is just something, you give it a signal, and it manipulates this signal to produce some output signal. Now, systems also come in class. So there are types of systems. So we have the linear versus nonlinear classification of systems. And so linear, for a system to be linear, it must satisfy a very strict mathematical condition. And if this mathematical condition is not satisfied in any way, then the system is nonlinear. And if you read the condition, you'll find that the condition is a tough condition. In other words, that there is no linear system. You cannot find in the whole universe a linear system. It's a fiction. It's a fictional system. Okay, every system will be nonlinear. But then good news is that many systems, behave very close to linear systems, to the abstract or the theoretical linear systems. Okay, so it is not that in reality we can find linear systems, but many systems are close enough so that we can apply the theories of linear systems and get very good, let's say, predictions about how the system behaves and so forth. Okay, so I will use, rather than, saying that we will give the system an input x of t or x of n, and then the system will respond with the output y of t, y of n, I will just use this notation here. So this notation here means that the system is fed with x of t, and in response, the output is y of t, and this is the story for discrete time systems. Okay, so what is a linear system? So a system is linear if, okay, basically you have two inputs, x1 of t, giving the corresponding output is y1 of t. Another input x2 of t, the corresponding output is y2 of t. Okay, the system is linear if basically the system responds to this linear combination of x1 of t and x2 of t with the linear combination of those outputs y1 of t and y2 of t. So you ask yourself, what will the system do if I do not give it just x1 of t? We know that if you give it x1 of t, it produces y1 of t. If you give it x2 of t, it produces y2 of t. What if you give it some scalar constant multiplied by x1 of t plus another scalar constant multiplied by x2 of t? What will be the output? A linear system will do this. A linear system will produce as an output the signal alpha 1 y1 of t plus alpha 2 y2 of t. And it will do so for every possible x1, x2, alpha 1, and alpha 2. If it does so, then the system is said to be linear. Otherwise, the system is nonlinear. Okay, so this is basically linearity. Again, linearity is not that there exists some input x1 and some input x2 such that if you give the system a linear combination, it will give you a linear combination of the respective outputs. This should be true for all linear combinations and for all possible input signals x1 and x2. Any violation will be, so if you can find any violation to this definition, then the system will be non-linear. Okay, so this is the, this is the linear system. So as a special case, of course, a linear system, if you give, so if the system is linear, so if the output is y of t in response to x of t, okay, so as a special case, what if you scale the input? Okay, so it's as if, again, it's as if we are applying this definition here with alpha 2 equal to 0. So what if you give it an input, it gives you an output? If the system is really linear and you scale the input by an amplitude factor, that is just a constant, it does not depend on time, then it should respond with alpha y of t. Okay, so this is, this is an implication of linearity. Okay, but linearity is a stronger thing. Basically, this is the full definition of linear. It must basically obey this definition to basically qualify as a linear system. Okay, so this is like examining whether a system is linear or not is better done using examples. I will do a couple of examples here, and on Blackboard you will find, like, again, like more examples, and I am sure that you can find more examples in in references online, and so forth. Okay, so here is our system. Okay, so it's y of t is equal to some constant x of t plus some other constant. So this basically system, it takes a signal, it multiplies the amplitude of the signal by some given constant c, and then it adds sort of a bias or something which is d. And the question is, is this system linear or not? So you give the system x1 of t. From the definition of the system, this is the description of the system, from how the system operates, basically, if you give it x1, it will scale x1 by c, and then it will add d, and this will be y1 of t. If you give it x2, it will multiply x2 by c, then add d, and this will be y2 of t. So now the fundamental question that is relevant to determining whether the system is linear or not, what will the system do if now you give it this guy multiplied by some constant alpha 1 plus this guy multiplied by some constant alpha 2? So what if you give it this signal here? Now, according to the system description, regardless of the input, this system does the following. It takes whatever input, multiplies this input by c, and then it adds d. Okay, so if you give it this linear combination, it doesn't care whether this is whatever, anything that is fed to the system will be multiplied by C, and then D is added. So basically the result here will be C alpha 1 x1 of t plus C alpha 2 x2 of t plus D. This is something, this is what you obtain from, this is not magic or anything. This is actually what the system is doing as described in the problem statement. Now, if the system is linear, if it were linear, okay, what should be the output? So this is the actual output from the system. So this is the actual output that you get, again, based on how the system is described, how it operates. If the system were linear, basically what you should get in response to this input is the same linear combination applied to these two guys, y1 and y2. So if the system, if linear, the system should give you alpha 1 y1 of t plus alpha 2 y2 of t. Okay, so for the system to be linear, so if linear, so this is not an actual output of the system. This is the output under the assumption that the system is linear. And this is the actual output. The system is linear if these two guys are the same. So for the system described in the problem statement to be linear, it must be the case that this output here that we obtain from basically knowing how the system works, this should be equal to the output that you expect from a linear system, which is this expression here. And by comparing the two expressions, you will find that basically this term is like this term is like this term, but then we have a trouble here because this is the actual output. So let's put these terms here. So this is actual output, and this one here is output if system is linear. So this is what you get from the definition of linearity. And by comparing the two guys, you will find that these two guys are the same if D is 0. If D is 0, okay, so if the bias added by the system is 0, yes, the system is indeed a linear system. But if you have a D, then generally speaking, this term is not equal. So this term here, this plus D will not be equal to this term here, which is alpha 1 plus alpha 2 plus alpha 2 D. Right? Now you may say that the actual output and the output if the system is linear, the outputs are equal if the parameter alpha 2 is minus alpha 1. Okay? This is true, but it does not mean that the system is linear, because the system is linear by definition for all possible values of alpha 1 and alpha 2. Setting alpha 1 or alpha 2 or both to specific values does not mean that the system is linear. So you can satisfy linearity for specific values of alpha 1 and alpha 2 and x1 and x2, but this does not mean that the system is linear, because the system is linear by definition if basically this property is satisfied for all scalars, all x1 and all x2. So you cannot come here and say that, we can make basically this term equal to that term by choosing alpha 1 plus alpha 2 equals 1. Okay, alpha 1 plus alpha 2 equals 1. If the sum is equal to 1, sorry, I said the sum equals 0. No, I misspoke. It's 1. If you make alpha 1 plus alpha 2 equals 1, you will get a D and a D, right? But again, this is not, you are constraining alpha 1 and alpha 2 to basically obey this equation that their sum is 1. But the definition tells you that you should get equality between the actual output and the output that you expect from a linear system for all possible x1, x2, alpha 1, alpha 2. Okay, so in our case here, our system is linear if and only if D is equal to 0. Okay, so d is not equal to 0, then the system is a nonlinear system. Despite the fact that if you look at the relationship, it may look that the relationship between y of t and x of t is linear, right? You take x of t multiplied by a number and then you add d. But according to the definition of linearity, this is a system is linear only, and actually it's if and only if d is equal to 0. Otherwise, it is nonlinear. Let's examine another system that basically takes a signal and it multiplies the signal by some given function phi of t. Is this system linear or not? So again, the system, you give it a signal x of t. The system locally generates a function phi of t, and what the system does is that it takes x of t, regardless of what it is, and it multiplies it by phi of t. So if you give the system x1 of t, it will respond with y1 of t, which is x1 of t multiplied by phi of t. You give it y2 of t, it responds by x2 of t multiplied by phi of t. And from the system description, if you give it this linear combination, it will respond by taking the linear combination, or taking any input, and basically multiplying this input by phi of t. And so what this is the output based on how the system operates. Now you can write this output as alpha 1 phi t x1 of t plus alpha 2 phi of t x2 of t, which is alpha 1 y1 of t plus alpha 2 y2 of t. So that's the same linear so the linear combination applied to the inputs, is here, applied to the respective outputs. That's the test of linearity. And basically there is no constraint here. X1 can be anything, X2 can be anything, alpha 1, alpha 2 can be anything. And so basically the test of linearity is, it's okay. Here there are no violations or anything. This system is indeed a linear system, regardless of phi of t. You multiply, so a system that takes a signal and multiplies this signal by some given signal is a linear system. Okay? I am doing the business here using continuous time signals. There is no fundamental difference if we talk about discrete time systems. Okay, so again, like doing things here in continuous time is not like that. Discrete time, they have like a different theory or anything. It's exactly the same for discrete time systems. Now, another classification of systems is, rather than linear versus nonlinear, we talk about systems that are time invariant or time varying. Okay, and again, time invariant systems are fictional. Okay, let's see how they are defined. A system is time invariant so you give the system the input x of t, it responds with y of t. Now, the system is time invariant if you shift the input by any shift. What happens to the output is that the output will be shifted by the exact same shift, and nothing else will change in the output. So a system is time invariant. You give it some input, it responds with a certain output. You shift the input. What will happen to the output is that it's the original output shifted by the exact same shift in the input. So this is minus t0, this is minus t0. And this should be true for every x of t and for every shift, whether, so t0 can be any real number, whether it's positive or negative. So if this is satisfied, our system is time invariant. Otherwise, the system is time varying. Okay, so let's basically do the example that we studied, and we showed that the system is linear. Now let's investigate whether the system is time invariant or time varying. So again, it's our friend that takes a signal and multiplies this signal by a specified function. So one example of this is the up converter in any transmitter for a communication system or a radar system. So basically, we have the so-called baseband signals, and to transmit those signals, we upconvert them. We multiply them by something like cosine by 2 cosine 2 pi f carrier. So this 2 pi f carrier t, or sine 2 pi f carrier t, where f carrier is some given carrier frequency, 1 gigahertz, 2.4 gigahertz. It varies from system to system. So that's an example of a system, again, in which you take a signal and you multiply it by a given function. And so in those systems, there is a local oscillator that is basically producing sinusoidal signals with the fundamental frequency f carrier, and those generated signals are multiplied by whatever input, and the input in those communication or radar systems will be like basically pulses carrying information, and so that's so this is not a far-fetched system. Actually, communication systems are like this. They have a component that basically does this thing here. This system is linear, but the question now is it time invariant? So let's do the test. Feed the system with x of t. The system will respond with y of t, which is x of t multiplied by phi of t. Now, suppose that you give the system another input g of t. Now, the system doesn't care. Regardless of the input, it will take the input and multiply it by this given function phi of t. Now, to test time invariance, let this other input be the shifted version of this first input. So let g of t be x of t minus t0, right? If the system is time invariant, it must be the case that in response to x of t minus t0, the output is y of t minus t0, and this is regardless of x of t and regardless of the value of t0. So let's see whether this is our case here. Okay, so in response to some g of t, the output, which I denote here as y bar of t, is phi of t g of t. Now set g of t equal to x of t minus t0. So what is this thing? So what is y bar of t? It is phi of t and then g of t. What is g of t? It is x of t minus t0, right? So this is actual output. So this is actual output based on how the system is characterized, how the system is described. So this is actual output. What do you expect if the system is truly time invariant? In response to x of t minus t0, it should give you y of t minus t0. And what is y of t minus t0? This is our y of t. It is phi of t x of t. So what is y of t minus t0? You replace t by t minus t0 on the left and right hand sides. And so this is y of t minus t0. So for our system to be invariant, again, what is this thing? This is output. This is not the actual output. This is output if system is time invariant. If it is time invariant, this is what you expect to get. This is actual output. This is actual output. If they are the same, then our system is time invariant. Otherwise, the system is time varying. So now, is it generally true that basically this is equal to that? Again, for time invariance, we need the two sides to be equal for any possible x of t and for any possible real number t0. So to have time invariance, this is x of t minus t0 and it is there. So basically, to get time invariance, you need phi of t, which is this guy here, to be equal to phi of t minus t0. And you need this for every t and for every t0. Again, according to the definition of time invariance, you need this to be satisfied. You know, it's not for a particular shift. It must be true for any shift. Okay, so what I can say is that a system that takes an input x of t and multiplies this input by phi of t, it's time invariant if and only if. So it is, you know, so basically we need a constraint on the function phi of t that is multiplied by the signal. Otherwise the system, you know, to be time invariant, you need this function to satisfy this. That basically phi of t is equal to phi of t minus t0 for every t and t0 that are real numbers. Otherwise, the system is time varying. Okay, so what is a function? What is basically phi of t? If phi of t is equal to phi of t minus t0 for every t and for every t0. Okay, so what to look at this is to say this is like the definition of periodicity. Okay, and it's like t0 is like a period, but you want this to be satisfied for every t0 that is a real number. So it's like we want a periodic function basically for which any non-zero real number is a period. And so what is the signal? It's the constant signal. Okay, so basically for this to be satisfied, we need our signal to be constant. Another way of seeing this is that this t0, so there is a t here, okay, which is some number, and t0, you know, you can vary t0. You want this to be satisfied for any t0. So if you put t0 equal to t, what you get is that phi of t from the left-hand side is equal to phi of 0 on the right-hand side, and phi of 0 is just a number, okay? And so we need phi of t to be equal to a number for every t. So again, this is another argument to say that basically, if you want time invariance, you should multiply x of t by a constant, which means that you do amplitude scaling, and that's it. If you multiply x of t by any function that other than the constant function, then your system is linear from the previous slide, but is time varying. Okay, let's take another example. So another example is this system. It comes with a given function psi of t. Now the system is this: y of t is equal to x of psi of t. So basically, if you want to compute what is y of 5, what is the output of the system, at t equal 5 seconds, if we measure time in seconds, then what you should do, the output at t equals 5, basically it is the input at psi of 5. So you need to take this 5 and feed it to the function psi of t. Let's say that psi of 5 is equal to 7. Then y of 5 is equal to x of 7. So y of t is not equal to x of t. Y of t is equal to x psi of t. Okay, so basically the output is the input. The output at time instant t is the input at time instant psi of t, where psi is some given function. Is this system time invariant or not? If the system x of t, it will respond with y of t, which is x psi of t. Give this system g of t another input, it will respond with y bar of t, which is g psi of t. This system will always do this, again, by definition, by how it's defined, by how it is characterized. Now, to study time invariance, this other input, g of t, we will take it to be the time-shifted version of x of t, which is x of t minus 0. So what will be the output? Okay, so now g of t is x of t minus t0. Means what? g of something, g of some real number is x of this exact real number minus t0. Okay, so what is g psi of t, which is a real number? We assume, of course, that function psi, of course, psi is a function from R to R. Okay, so basically g of psi of t, if g of a number like here is x of the number minus t0. Okay, so this will be y bar of t. So this is actual output. Actual output based on what? Based on how the system operates, how the system is described. Now, if you want the system to be time invariant, what is the output that you should get? Well, in response to x of t minus t0, the output should be the output in response to x of t shifted by the exact shift t0. So the output should be y of t minus t0, which is this thing here. So this is actual output, and this is output if system is time invariant. Do they look the same for every x and for every t0? No. Okay, they look different. On the left hand side we have x, and the argument of x is psi of t minus t0, and on the right hand side we have x, and its argument is psi of t minus t0. Okay, so if we want these two guys to be the same for every x, for every t0, it must be the case that psi of t minus t0 is equal to psi of t minus t0, so those two arguments are the same, and this should be true for every, again, t and t0 that are real numbers. So again, we have conditional time invariance. It's not that for every psi of t that our system will be time invariant. We need basically our psi of t to satisfy this functional equation. And this functional equation, basically, if you think about it, psi of t minus t0 is equal to psi of t minus t0. And again, this should be true for every t0. One way of doing it is to say, okay, what if we set t0 equal to t? So if you set t0 equal to t, then this becomes psi of 0. So here we put t0 equals t. Then, we do not have time invariance if this is satisfied for a particular t0. It must be satisfied for any t0. So you can set t0 equal to t. In that case, psi of 0 will be equal to psi of t, and we set this t0 to t, so psi of t minus t is equal to psi of 0, which is a number, which is the value of function psi at 0, and so psi of t is t plus this number, which is a constant. So our system is time invariant if, and only if, the function psi of t is t plus a constant. So for systems in which y of t is equal to x psi of t, so those systems, it's a family of systems depending on psi of t. So this system is time invariant if and only if it is a mere time shift. If it's a time shifter, right, it takes t, so basically if system y of t is equal to x of t, t minus tau, this will be a system that is time invariant. But if for example, if you do something like this, that y of t is equal to x of minus t, or y of t is equal to x of 2t, so it's time scaling and so on. So those are not time invariant. Those are not time invariant systems. Those are not time invariant systems. So those are time varying. So according to our derivation here, is that again is feed the system with x of t, you get an output y of t, and you know the output based on the description of the system. Give it another input g of t, get the output. Set g of t to be a shifted version of x, because this is what is relevant to time invariance. Now you have basically the actual output of the system based on the system's description. Now see what output you expect if the system is time invariant, compare, and from that you may discover that the system is time invariant, or it may be time invariant based on conditions. So it basically, if there are unknowns, for example, in this problem we are solving without knowing exactly what is psi of t. So now we obtain this condition that if psi of t is just t plus 7 or t plus or t minus 18 or something like this, if it's a time shifter, if it just basically does a time shift to the signal, then indeed it is a time invariant system. Otherwise it is a time varying system. Okay, so again, further examples in you'll find on Blackboard. And linear time invariant systems are basically systems that are both linear and time invariant. So based on what I described, there is no relation between these two classifications. So we have all four possibilities. So we can have linear and time invariant. We can have linear and time varying. We can have nonlinear and time invariant, and we can have nonlinear and time varying. Okay, so all you can find examples for all basically the four cases, because there is nothing telling you that that if the system is linear it must behave in this or that way. You can always find linear systems that are time invariant and linear systems that are time varying. Same story for nonlinear systems. Okay, so LTI systems will be systems basically in which these two guys are characterized, and if the definition of linearity is fictional, and incredibly, or like actually it's impossible to find in reality, let me tell you why. So in any system, let's say that you give a system x of t and it gives an output, let's say it multiplies the it gives some output, okay, y of t. Now according to linearity, if you scale the input, right, you should get the same scale factor in the output, right? So so suppose that you have an amplifier, so you give it x of t, and it produces some output. Now if you multiply the input, I mean, according to the definition of linearity, this should be true if alpha is equal to a trillion. So if you take an input signal multiplied by trillion, well, I mean, this is a signal that you cannot even create. But if you do, and you feed it to a circuit, to an amplifier circuit, basically the amplifier circuit will explode, right? So basically to insist that basically if you do amplitude scaling to the input, and you expect your output to follow over every possible amplitude scaling of the input, is fictional, right? Again, because the input itself, after a while, it will be high enough to basically, let's say, destroy your system or render your system basically useless or non-functional or whatever. Now for time in, yes, exactly, yeah. So for a range, yeah, exactly, for a range. So if you remember, if you took a course on circuits and you study those things, transistors and so, you will find that there is something called small signal analysis. So for amplifiers built with transistors, or many transistors in an operational amplifier and so on, yes, if your signal is millivolt or something like this, the amplifier will work. and it will amplify the signal, let's say, by some factor 10 or 100. But of course, if you increase the input signal, this small signal analysis will fail, because actually the amplifier will start to behave in a nonlinear fashion. Okay, again, so we have linearity on a range. Okay, so yes, so you can make this claim that for actual systems like amplifiers and so on, you can have linearity, you can have this satisfied on a range, but the mathematical definition is very harsh. It's like you should have this for every possible scale, amplitude scaling. For time invariance, it's sort of the same story. Like if you have an input, you give the input to the system. If you delay this input by 1 trillion years, the system to be time invariant, it should delay the output by 1 trillion years, but actual systems age. Actual systems will not last that long. Okay, so that's the reason, like, again, the mathematical definitions, because they insist on the linear combinations or the time shifts to be anything, to be any real number, or for amplitude scaling, you can actually extend it to complex numbers. It becomes clear that those guys will not be in reality. But the nice thing is that in reality we find systems under some particular situations, they will behave like an amplifier circuit. It will behave as a linear system. Not for every input. Again, if you increase the input sufficiently enough, you can actually destroy the circuit. But over some acceptable input range, it will behave in a linear fashion. Okay, so LTI systems are what you can call a useful fiction. They are a useful model. Right? All models are useless, but some are useful. So it is very useful, and so why actually insist on linear time invariance as a model? It's because it is very tractable mathematically. So you can say and do many things with LTI systems that you cannot do for other types of systems. One of them is that you can easily predict the output of the system, of a linear time invariant system, if you just know one piece of information, which is the output in response to a Dirac Delta for continuous time systems, or a discrete time Dirac Delta for discrete time systems. So for LTI systems, if you give the system, let's talk about discrete time systems, because we know that the Dirac Delta is fictional also. But for discrete time systems, the discrete time delta is a sequence in which you have 1 at 0, and everywhere it's 0. Now, if you know the response of the system to this particular input, you can basically you can compute or predict the output of the system to any arbitrary input. For other systems, for other types like this, things are not that straightforward. Okay, so let's see why LTI systems are like really good, like in terms of, again, tractability, mathematical tractability. So consider a discrete time system. It's LTI now, so it's basically both linear and time invariant. Suppose that you know this h of n, which is, again, it's not any output. It's basically the output if you get to the system. So basically, this is your system. You feed it delta n. And so what is delta n as an input sequence? It is 1 at 0, and then otherwise it is 0. So this is the input that you give to the system. So suppose that the system will respond with h of n. Okay, so this is what we know about the system. So just the output corresponding to delta n, nothing else. Now, suppose that you feed the system an arbitrary input, which is x of n. We will see now that we can we can basically predict or know what the output will be just using this h of n, which is called the impulse response. It's called the impulse response because it is what you get as an output if you excite your system with basically with the delta. With here it's the discrete time delta, and for continuous systems it will be the Dirac delta. Okay, so we will also discover that we will need like a further assumption. Okay, so and like things are typically difficult, and there will be a needed assumption that we will insert in there, and we will basically live with it. Okay, so sometimes we need like to be pragmatic. So first order business is actually to rewrite x of n using this expression here. Okay, so it may look like something that is like strange, but it is not. So I claim that x of n is basically this summation here, x of m delta n minus m. This is the discrete time delta. So again, let's, as a reminder, this delta k is 1 if k is equal to 0, and 0 if k is not equal to 0. Okay, so you have this summation. So fix an n, and there is the summation index running through all the integer values. Now, what happens with this Dirac delta? With this, it's the discrete time delta. Let's say discrete time delta. I mean, it's not a monster or anything. It's basically this, straightforward sequence. Now, basically, this guy is always a 0, except when its argument is equal to 0. So basically, m, if this index m is different from n, the discrete time delta is 0, and we have a 0 term. Only when small m is equal to small n, then the Dirac, basically, or the discrete time delta will be 1. And so basically, so this is 1 when m is equal to n. So the only surviving term in this infinite sum is when the summation index m is equal to small n, and in that case the term will be x of n multiplied by 1, which is x of n. Okay, so again, from sort of the definition of the discrete time delta, you can take x of n and express it in this, apparently complicated way, but it will be useful for our purposes. Okay, what do we know about the system? We know that if we know that it is, we take our system to be linear, we know that it is time invariant, and we know that if we feed it delta of n, the discrete time delta, it gives as an output h of n. Okay, so can you tell me what happens if you feed this system with delta of n minus m? So this is a shifted version of the input. Now, for a general system, if you shift the input, many things may happen to the output. But because our system is time invariant, then we know the rule. The rule is that any shift you do in the input will be reflected in the exact same shift in the output signal, and nothing else will change. So delta n minus m will give you h of n minus m. Again, this is something, so for continuous time systems, x of t gives y of t. So x of t minus t0 gives you y of t minus t0. Same is true for discrete time systems. You give x of n, to get y, and if you shift the input by any n0, then if the system is time invariant, the output is a mere shift of the input. If there's a shift here, it's there, nothing else, no amplitude scaling, nothing except this shift here. So any system that is not time invariant, you cannot say so. Okay, so for here, delta n minus m will give h of n minus m because the system is time invariant. Okay, now take this guy here and multiply it by x of m. So that's the value of the input signal at the mth, instant of time. Now our system is not just time invariant, it is also a linear system. And because it's a linear system, then if you do amplitude scaling to the input, you have the same amplitude scaling applied to the output. Again, if the system is non-linear, then this is not generally true. But we know that this is true because basically our system is linear. So now we know that x of m, if you take this as a number, multiply by delta n minus m, you will get x of m, h of n minus m, again exploiting the LTI, basically property of the system. And this is true for any shift m, which is some integer. Okay, so basically x of 0, delta n, will give x of 0, h of n. X of 1, delta n minus 1, will give you x of 1, h of n minus 1. X of minus 1, delta n plus 1, will give you x of minus 1, h of n plus 1. X of 2, delta n minus 2, will give you x of 2, h of n minus 2. So basically, again, what I said is true for any small m that is an integer. Now the system is linear. The system is linear, right? So for a linear system, its definition is based on basically a linear combination of two inputs. You can use something like induction and show that basically if you have a linear combination of any finite number of inputs, then you will get the same linear combination of the respective outputs. Okay, so the linearity of the system means that we can sum, those inputs on some finite. So basically, we sum over the m values taken from a finite subset of the integers, and indeed it will give us the correct, the same linear combination of outputs. But from the definition of linearity, extending it to infinite sums is not straightforward. Okay, so again, if we say that, can we basically do this summation over everything? No, it is not guaranteed that actually it will be true. So the definition of linearity does not involve infinite linear combinations of inputs. We start with 2, we can extend it to a finite, basically a linear combination of a finite linear combination of inputs. So basically a linear combination involving a finite number of inputs. So for example, you can say that, if the system, you give it x1 of n, it gives y1 of n. You give it x2 of n, it produces y2 of n. x3 of n gives y3 of n. Then, then if you give it alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3, if the system is indeed a linear system, then this will give you alpha 1 y1 plus alpha 2 y2 plus alpha 3 y3. And you can do so for any finite number of inputs, but actually we are greedy. We want actually to make this summation over the integers. Why? Because if we sum over the integers, this thing here will exactly be equal to x of n, as I argued. Okay? So we will assume that our linear time invariant system is not just linear as defined previously, but also its linearity extends to infinite linear combinations of inputs. Again, this is not linearity, as defined. Again, here we are extending it. We are sort of assuming that our system is not just linear, it is sort of like it has extended linearity in which also an infinite linear combination of inputs will give you the linear combination of the respective or the corresponding. So this is an assumption. If we do this assumption, then we can actually sum here from minus infinity to infinity. And what is this thing? It's nothing but x of n. So now x of n will produce this output here. So what is the conclusion? For systems that are linear and time invariant, and note that both assumptions are needed, because in the derivation, we exploited time invariance to justify going from here to there. Without time invariance, we are not justified in doing this step. To say that delta n produces h of n, so delta n minus m generates h of n minus m, and this is true for any time shift m, this requires time invariance. Then to multiply by x of m and to say that, basically the output will be x of m multiplied by h of n minus m, this requires linearity. But then, we have a bunch of basically inputs and the corresponding outputs. And what if we sum the inputs? Now, if you take any finite number of these inputs, nothing actually is needed other than linearity. But what if we want to sum over all those inputs so that we have as our input x of n itself? Then you need to push things further and make some assumption regarding our system, okay? Which is that actually we can do this. Basically extend linearity to infinite linear combinations, and the practical systems typically will allow basically this assumption. So this is when I talk about LTI system, you can just assume that it has this sort of extended linearity, which will allow us to say that if the input is x of n, then the corresponding output is this summation here, which is interesting because it tells you that an LTI system with this extended linearity, if you know h of n, if you just know how the system responds to a discrete time delta, you can actually use this h with any arbitrary input to compute the output of the system corresponding to that input. Okay, so this is very powerful. So the system now is fully captured by the so-called h of n, the impulse response. If you know it, that's it. You can compute the output in response to any input. Okay, and again, to derive this result, we needed linearity, time invariance, and actually extended linearity. And this summation here of x of n, this is denoted by x of n, and then this is star h of n. This summation here is the so-called discrete time convolution. Okay, so the output of the discrete time, the linear time invariant system, will be the convolution between the discrete time convolution between the input and the impulse response, where this discrete time convolution by definition is this summation here. And story can be applied to continuous time systems. So the continuous time system that is LTI with linearity being, this extended, it's fully characterized by its response to a Dirac delta, the impulse response. If you know h of t, so delta t gives you h of t, then what is x of t? Well, if you want to compute the output, is the convolution between x of t and h of t. So this is the continuous time convolution. And this convolution, again, by definition, is basically an integral that looks like this. H of t minus u du. Okay, so now, because of this assumption of extended linearity, there are LTI systems. There are LTI systems that you cannot characterize by an impulse response. Again, there are LTI systems that you cannot characterize by the impulse response because you cannot basically use the concept of extended linearity. So you can find examples for these in like books on functional analysis and stuff like this. These systems are not relevant to this course. Okay, so to us, LTI, if you see the word LTI, it automatically means LTI with extended linearity. It means systems that can be fully characterized by an impulse response. But again, I emphasize, you can come up with examples for LTI systems that satisfy the condition of the original definition of linearity and the definition of time invariance, and those systems cannot be basically their operation, their behavior cannot be captured by an impulse response function. Those systems are not of interest to us. Here we will assume, once you hear LTI, you will automatically mean it, take it to mean that there is an impulse response, and we can, knowing the impulse response, we can basically obtain the output by doing a convolution between the input and the impulse response. And this convolution, which takes this summation form, or for continuous time systems, it takes this integration form, okay, it will give you the output. Okay, so now what should we do? We should basically focus on this convolution thing. So convolution is again the name given to basically this summation that we have here, and the corresponding integral if we do basically continuous time systems. And so what are the properties of convolution? Okay, again, the importance of convolution, it stems from, it is the operation that if you do to an input signal and to an impulse response, you will get the output of an LTI system.